Hey,
What's happening?
Not
Hey,
much.
Dr. Needham, how are you?
Yeah, we got several folks.
Yeah.
Hi, how are you?
Hey, Juan,
How
how
you
are
doing?
you?
What's up? I at my home now. Hi, Mr. Sam. How you doing?
Good. How are you doing?
Good.
I miss you.
Miss you guys too.
Oh, it's fun.
Uh-oh, Justice is about to log in.
How can you tell?
It says Justice C. Brown connecting.
Oh, I don't. Oh, there it is. Yep.
Yeah, there it is. That's how he spells his name. I didn't even know.
Yeah, he's got a weird name.
I feel bad because he's not even, he can't even reply.
He should be on now. Maybe.
Oh no, he finally unmuted himself or got connected to audio. There he is.
Can I be heard?
Yeah.
Mr. Sam.
Yeah,
Cool. Wow, John, you're real big right now.
I know, right?
Justice, are you there?
Yeah, he's on chat.
Yeah. Oh, sorry, everyone. I meant Justice.
We are here. Or I'm not sure if everyone's here.
Got a red solo cup, Professor?
It is
Partying
something
already?
close to that. Yeah. That's Fanta or something in here. Honestly.
Wink.
That's what's actually in the water bottle. That's what's actually in the coffee.
I'll tell you what's not linear is the graph associated with my alcohol intake over the past 2 weeks.
All right. How's it going?
Pretty good.
Right.
What
Still
you guys want to
alive.
talk about? You're still alive. Yeah, that's the good news, I guess.
That's a good question.
Yeah, I didn't have exactly an itinerary, but I think that probably touching on each of like the core concepts for these upcoming sections
Yeah.
would be good.
I do kind of have an itinerary, but I just thought I'd throw this out here first.
Yeah, no
Sure.
doubt.
Well, first off, before we leave inverses, how do you feel about inverses?
Real good, I think.
If it's a 2x2 matrix.
Yeah, if it's a 2x2 matrix, that'll be.
That's the only size you like?
Well, the 3x3 one is difficult. If you're doing it by hand, at least.
It is tedious.
Yeah,
Takes some time.
Yeah. Not undoable, just tedious.
Fairly straightforward, though, I think.
Yep. What's the best way of finding an inverse?
Putting in your calculator.
You got it.
Can't argue with that.
Okay. And then don't forget your math, enter if you need to.
What's that?
Don't forget your math, enter if you need fractions.
Oh, yeah.
But just like with row reduction, where 95% of the time your calculator can do it, if you have an unknown or something, your calculator goes on strike, then you're kind of stuck. Regarding inverses, there are a few different ways of finding them, and some people actually gave me some in the homework. There are fancier formulas involving what are called the adjugate matrices and stuff like that. And good heavens, I didn't expect anybody to go that route because we hadn't talked about that stuff yet in class, and that just wouldn't be fair. If you want to do that, that's fine. But I think if you're just after an inverse, don't worry about those fancy formulas. Just learn how to do that row reduction algorithm.
Okay.
Anything else about the inverse? So the key with the inverse is that when you think about the linear transformations underneath them, the matrices of the inverse transformations are actually just inverse matrices. It just goes along like you would expect.
Okay.
Okay. And for something, any function in general, to have an inverse, it has to be 1-to-1 and onto.
Right.
And what size matrices can correspond to, or sorry, what shape matrices can possibly correspond to 1-to-1 and onto transformations? Only the square ones. Okay, so that's why only square ones can have matrices, or can have inverses, but not all of them do.
Okay.
I knew that was just as a shoulder. So questions on inverses?
I think I'm solid on those, to be honest.
Okay.
Yeah.
I think today's the deadline for the homework. I think everybody I see here has
Correct.
already sent it. If you have not, get your homework to me by like midnight tonight. Okay. If no one has any problem with it, I think I'm going to give you an effort grade on this one. And if you turn it in, I'm just going to give you 10 out of 10 points.
Hey, cool.
Hey.
Thanks.
Not
Mostly
mad about that.
because I don't feel like printing out 400 pages and grading them.
Well, fair
I
enough.
understand.
But I figured you guys wouldn't
Fair
complain.
enough. Fair enough.
So get me that if you haven't. All right. So like I said, I do have a little agenda here. We can at least hit the good kind of spots. Let me move this around here. And I actually did a class this morning for finite, and it went surprisingly well, but that's not to say it was awesome. I'm still learning how to use all this technology. If I'd known we were going to have a plague, I would have bought a better laptop. This is a little engine that could. So let me go ahead and share my screen. This one. So I think the first topic that came up, and I think we're looking at 2.8 now. Can you all see like a Word document with some blue pictures on it?
Yeah.
Yes.
Okay. So the first thing I talk about is the notion of a subspace. So a subspace is a subset. Do we all know what a subset is?
No.
No.
No, not
A
really.
subset, or heck, maybe I should write this. So a subset, let me see if I can sneak in. Ooh, see if I can do this. There are so many tools available in here, they start stepping on each other's toes, but we'll see. Draw. Oh, no, I don't want that one. I want this one. Annotate. Okay. So a subset. What are you doing there? Oh, this is freaking me out now. A subset. I don't know why I did that. It looks like a kind of a sideways C with a line under it. Okay, so I forgot an S. So a subset, we say A is a subset of B if everything in A is also in B. So a subset is just a smaller piece of a bigger set. So if everything
Professor, are you able to type instead of just writing with your hands?
maybe. I don't think I can do it here though, but I can try.
It's not hard to get what you're
Let's see. Let's see if I have this. Disable end meeting polls. I don't think I do here, but I might have it. The thing is, typing mathematics takes forever.
Oh, you can hit enable content and just start typing. I don't know.
Insert. Text box, I guess. Okay. Not what I wanted. This laptop's trying as hard as it can.
Yeah, it is.
I guess the answer is no. I'll see if I can figure it out for the next time. Basically, if everything in A is also in B. Okay. So if we have two sets, one's a subset of the other if the smaller one is actually a piece of the bigger one. So like the integers are a subset of all real numbers, because every integer is also a real number. Real numbers are a subset of complex numbers, because also every real number kind of corresponds to a complex number, and so on. Okay.
Could you repeat that?
The examples. So like every integer is a subset of the real numbers,
Okay,
because everything that's an integer is also a real number.
gotcha.
Rational numbers are also a subset of real numbers, because everything that's rational is also a real number. Fancier ones, because every differentiable function is continuous, the set of differentiable functions is a subset of the set of continuous functions. Okay. So for a subspace, look at these blue examples that I have here. They all happen to be non-examples, which means they are subsets, because every blue thing that is here is a subset of that R2 that we're looking at, right? That kind of that square there that I think is even intended to kind of go on forever.
Right.
It's a subset because everything in there is an R2. Okay.
Right.
Same is true for all of these. They're all subsets of R2. But the key thing for a subspace is that not only is it a subset, but if we take two things in that set and add, or sorry, in that subset and add them, we get something else back in that set. That's what this means right here. So for each U and V in that H, the sum is also an H. For each U in H, every scalar multiple of that thing is also an H. So the fancy way of saying this is that H is not only a subset, it is also closed under these two operations. So for example, if I were to grab some vector right here, like that, okay, what happens when I start scaling that thing?
Extend.
It extends that way with the positive scalars. But what about with the negative scalars?
It goes to the third quadrant.
I also get this. That's
Negative.
right.
Yeah.
Okay. So that thing can't be a subspace because I can multiply that vector that I chose and leave that space.
Right.
In fact, in Rn, there are only, all the subspaces kind of look pretty similar. So if you think about it, if you have some vector in R2, in order for that subset, whatever subset you're looking at, to also include all the scalar multiples, it has to include the entire line that that thing is sitting in, right? That's all scalar multiples. So basically, every line that passes through the origin is a subspace. And in this one, what happens if I add like a second vector?
Then all of R2.
Yes, so that line also has to be included. Pretend that's a line. Okay. But what happens when I start adding those two vectors? I get all of R2.
Anywhere. Yeah.
That's right. Okay. So in Rn, the only subspaces, so there are two easy ones that are kind of, the trivial one is this, the set that is only the origin. Okay. So that is a trivial subspace of any R whatever. You take the zero vector and you multiply it by stuff, you don't go anywhere. Okay. The other extreme is in Rn. Rn is technically a subspace of itself, but it's kind of a stupid way of saying it, but technically it fits the bill. Okay. The only things between the two extremes are actually lines passing through the origin, planes passing through the origin, and, you know, as you get fancier, you call them like hyperplanes and stuff like that. So for these non-examples over here on the left-hand side, so for example, in number 2, it does kind of look like it includes, so if I just grab something, you know, arbitrary in this set and start multiplying by scalars, although the blue thing kind of stops, I think they kind of indicate for it to go on forever up here in the first quadrant. So here, let's look at the first and the third quadrant. It also includes stuff down here. Okay. But those two quadrants aren't like a nice, complete, self-contained set, flat set going through the origin, because why?
Because the negative quadrant, or the negative x quadrant and the negative y quadrant.
Well, they're covered by scalar multiplication, because if I take one of these in one of these quadrants and multiply by a negative scalar, I get something in the other. So I'm kind of covered that way. But what happens if I take like that vector right there, and if I take a vector kind of just underneath that right there and I add them? What do I get?
Then they add to the second quadrant.
And I get something in the second quadrant. You got it. Okay. So in number 2, the set they gave us is actually closed under scalar multiplication, but it's not closed under vector addition. So it is possible to take 2 things in that set and add them, and you leave this set. And for a subspace, you can't do that. Okay. So again, in Rn, the only real subspaces are lines, planes, and, you know, all those big flat things that pass through the origin. This one doesn't work, because if I take that and start scaling, I can eventually leave. That one doesn't work because I can scale in the negative direction and leave. I think the only one that's closed under scalar multiplication is number 2, but it's not closed under vector addition. So again, the only options in R2 that are examples: the trivial subspace, any line passing through the origin, and the whole darn space. So when you're working in a subspace, you know that you can like you can do all these linear algebra operations, multiplying by scalars and adding stuff, and know that you're just going to continue to live in that space. You're not going to leave it.
Okay.
Got it.
Questions?
So are these vectors that we're talking about yet, or are we just talking about like general spaces within a larger space?
And in this case, we're thinking about those spaces as being made up of vectors. You can get fancier with vector spaces, which we might talk a little bit about later on. It depends on how this semester goes. It's one of the topics that I can leave out. But mathematicians kind of get fancy with it, and they kind of generalize the notion of a vector and a vector space. But the idea of a subspace is that it is a smaller piece of the whole thing that is completely self-contained with vector addition and scalar multiplication.
Okay.
So when we're talking about, from what I understand in these rules here, U and V we're referring to are vectors, C is a scalar. What exactly is H? Is that just like an arbitrary
H is your subset. So in the example, the non-examples they gave us over here, H is the region that's colored blue.
Mm-hmm.
So that is a subset of R2, because everything in this region is also contained in the whole thing, but it's not a subspace. Same here. Those 2 quadrants are a subset because everything in there is also in R2, because they drew it that way, okay? But it's not a subspace. All these blue regions are actually subsets, but they fail to be subspaces.
Okay.
So essentially, subspaces are only full dimensions within another. So like
yeah, I know what you're after. Yeah.
So like a subspace. So like R2 would be a subspace of R3.
Yes.
And R2 would be a subspace of Rn plus 1.
Right. Technically, it's isomorphic to a subspace, but I know exactly what you mean, and you are correct.
Okay.
Yeah. So, for example, if we're looking at something in R3, X, Y, and Z. Okay.
Yeah.
Any plane passing through the origin is actually a subspace. Because if you think about it, if you grab any 2 things in there and start scaling them or adding them, you get something back. But if you have a plane that does not go through the origin, this is actually a theorem in the book. If you have a set that does not contain the origin, it can't be a subspace. Because what scalar can I multiply something by, and I have to be guaranteed that it gets me back in that set?
0.
I can multiply by 0, right? So if I take any kind of vector at all, let's just say, hey, I have one vector. I'm just looking at the vector there, okay? If that vector is in some subspace, then when I multiply that vector by the scalar 0, the result has to be in that subspace. Therefore, 0 has to be in there. Okay. So actually, if you're looking at a set, and you look and see that it does not contain the origin, you can stop. It can't possibly be a subspace. And that is one kind of, it is often the easiest way to tell that something is not a subspace. If it does not contain the origin, it can't be a subspace. But just because it does, doesn't make it one. Like these examples here, they all have the origin in them, but they still fail to be subspaces. Okay,
And so if the
go ahead.
If the actual vector, so if the actual matrix itself doesn't contain the origin, then that wouldn't be necessarily a subspace of the dimension that it's in.
What do you mean by a matrix not containing the origin?
So like a matrix could be, so a matrix is a group of vectors.
Yep.
So say it doesn't span the dimension that we're working in. Right?
What you mean like your columns of your matrix?
Yeah.
Yep.
So,
Okay.
So that doesn't span the dimension that we're working in.
Uh-huh.
That would be that's a subset, but not necessarily a subspace.
Well, that actually kind of leads me to one of our next topics.
Okay.
Okay. So if you look at the span of any set of vectors, because the definition of a span is what? It's all the linear combinations of those vectors.
Mm-hmm.
Okay. So think about it for a second. If I have a subset that's a span of some vectors, okay, that span includes all scalar multiples, so it's closed under scalar multiplication.
Mm-hmm.
If I take two things in that set and add them, that's a linear combination, so that must also be in the span. Okay. So if you have a set that is actually a span of some vectors, it's got to be a subspace.
Cool. All right.
And what you just mentioned, I think it was David, judging by the voice, is that when you have, or when you look at the set that is spanned by your columns, it is a space because it's a span, and in fact, that is what is called your column space. It is a fancy name for what we have been thinking of as the range of the linear transformation. It's the set of things that you can get out when you multiply by that matrix is the set of linear combinations of those columns, which in this fancy terminology, we would just call the column space. In fact, I think I have that on the next page here. Let's see, let me clear this. I will make this video available later. Oh, shoot, hang on, I'll be right back. Stop share. Hey, John.
Hey.
Whoops. Yeah, I blew it. I did that too soon. There we go. Okay. Okay. So my second page, yeah, so that first thing is what I just said. So any set that is the span of some vectors is a subspace because it's built by taking all the linear combinations, and that's kind of what it means to be closed under vector addition and scalar multiplication. Okay. Any Rn has two easy subspaces, 0 and Rn. They're kind of like the trivial ones, and all the others are flat, infinite spaces that pass through the origin. Okay. So associated with any matrix, there are a few like big subspaces. Okay. The three that we're going to talk about are the column space, which I just kind of defined. It's the span of the columns of your matrix. In other words, it's the range. Okay. The null space, which I'll write the definition down here in a second. The null space is the set of things that land at 0 when you multiply by your matrix. And then your book doesn't talk about it till later on, but it's easy, so we may as well do it as something called the row space, which is the span of the, anybody want to take a guess at it?
Rows?
Smart ass. It's the rows. Yep. Okay. So the key is, how do you find these subspaces? Well, we haven't yet talked about a basis. That's coming very soon. Okay, that's in the next section. So right now in 2.8, before we talk about a basis, the only real things I could ask you is, hey, is such and such in the column space of this matrix, or is such and such in the null space of this matrix, or is something in the row space? Okay, I'm going to be more interested in, is something in the column space or something in the null space? So before we get into 2.9, oh no, I guess they do talk about basis in 2.8, right? In 2.9, I kind of,
Yeah.
I put 2.8 and 2.9 together in my head. 2.9 is like coordinates. So in
2.9
2.8,
is
so before we
dimension.
talk about a basis, let's do this. Let's see here. Let's see if I can stop this and bring up a whiteboard. Okay, share screen. Whiteboard.
Nice.
Okay. This will work. All right, so I also got something else going here. Hang on a second while I look at my other monitor. So instead of me just making stuff up, let's see. Okay, well, let me write down the definitions first. That would probably be best. Whiteboard Zoom. Okay, so the column space. Oh, that's terrible.
Checks there.
Yeah.
So the column space, COL, not CD. I also have one of these Wacom tablets I'm learning how to use.
Column space.
Okay, so the column space, COL of A, okay, that is just the span of the columns of A. So in a little bit, once we talk about a basis, we will come up with a way of basically finding kind of everything in that column space. Span of A's columns. I meant to say columns of A.
Is the column space identical to the span of the columns of A?
Yep.
Okay.
Oh, come on. Span of columns. I forgot an N. Of A. Okay. Which is also equal to the range of that linear transformation. That kind of, we think of, linear transformation that takes things and multiplies them by 8. So the range of the linear transformation. Okay, they're the same thing. So for example, if I had something like, let's see, let's let A equal, I don't know, 1, 3, 0, 4, 0, 1, minus 1, minus 1, 0. Okay. One question I could ask you is, hey, here's a vector. Is it in the column space of A or not? Okay, so is 3, 1, 1 in column space of A, and let's just say leave it like that. Okay. So in other words, is 3, 1, 1 a span, or sorry, is it a linear combination of my columns of A? So I have to see if I can find what on my columns? Weights, right?
Mm-hmm.
So basically, I just end up doing this. I take the matrix that I started with, and I am trying to see if I can use the columns to get to 3, 1, 1.
We just kind of augment it with 311 and reduce then.
That's what I did. And now I do an RREF on that 3x4 matrix. If I have a solution, yes, it is in the column space. Okay. If I don't, no, it's not. So just one more way of kind of asking, hey, can I solve these equations? Is the vector I'm trying to get to in the column space of my matrix or not?
And if it's not, it'll come up like undefined or something, right?
Well, you'll get 0, 0, 0, 1 on the bottom.
Oh, yeah. Okay.
Okay. In this case, off the top of my head, I don't know for sure. I think it probably is. Okay. So I would do this solution, or no, hang on. I have a fancier word for this. So if it's consistent, hang on, I'm looking for my mouse. Okay. So consistent means yes, it is. Inconsistent means no, it's not. And I'm just going to leave it like that. Okay. So for right now, just to decide if something is in the column space, all you do is augment with that vector and see if you can solve it. Easy enough?
Yeah.
Yeah.
Okay. So it's just like a different terminology for what we've been doing with, you know, can I get there? Can I solve them? Is it consistent or not? I'm looking at the text to see if there's anything. If I no, oh, so in your textbook, I don't want to stop sharing and go back to this, but well, hang on. I'm going to go back to the book here in a second. Bear with me. Stop share. Share. Is it this one? Okay. So you see my book again? So look down here.
Yes.
Look down here at 5 and 6. So they kind of phrase exactly the same thing differently. So in here they say, let V1 and V2, I'm looking at number 5, right here. V1 and V2 are two vectors that live where? R3, and they give us some W also in R3. They say determine if W is in the subspace of R3 generated by V1 and V2. Well, I didn't tell you what the word generated by means, but what do you think it means? V1 and V2 are some vectors, and what's the subspace generated by those two vectors? It's just the span of them, just a different phrasing for the same thing, okay? The subspace of R3 generated by V1 and V2 is just a span of V1 and V2.
Okay.
So now with that in mind, how would I determine if W is in the subspace spanned by V1 and V2? Well, I'm just saying I'm asking, is W a linear combination of V1 and V2? So what do? I set up a matrix and augment with W and see if I can solve it or not. Same exact thing, just different way of phrasing it.
I've got a question.
Go.
So isn't it always going to be like for number 5? As long as V1 and V2 aren't linear combinations of each other.
As long as they're not?
Right. If they're not like, if they're pointing in different directions, I guess I'm thinking about it graphically.
Sure.
So like if the vectors point in different directions,
Uh-huh.
doesn't that mean you can get to all the points in R3?
Well, I would need, since they're in R3, but I only gave you 2 of them, those 2 vectors
you would need
best
a third vector.
Were 1 short. That's right. Yep.
Okay.
But if I gave you 3 vectors in R3 that were linearly independent,
right,
then the subspace they generate is, ta-da, all of R3. You got it. If they're not linearly independent, then the subspace they generate is some smaller subspace. It's either a plane or a line through the origin, depending on how dependent they, oh, there's a lousy phrase, depending on how dependent they end up being.
Okay.
So for number 6 over there, same thing. They give you 3 vectors in R4, okay? So they can't possibly span all of R4, so it's not a trivial question, even if they are independent. At best, if they're independent, it spans some 3-dimensional subspace, okay? And what I would do is I would make V1, V2, and V3 columns of a matrix and augment with what? U, and see if I can solve it or not. Yep. If you can solve it, it's in the subspace. If not, it is not. Any other column space questions?
I don't think so.
Okay. So basically,
Over
column
here.
space is just another term for the span of the columns or the range of the linear transformation. Okay, so another one of the big spaces. Let me go back to a whiteboard. Let me see here. Nope, hang on, go back here. Stop share. Share screen, whiteboard. Okay.
Professor,
Yo,
are you gonna post the homework 5 solutions, or did you already do that?
I have not yet. I'm waiting. I think I'm waiting till midnight because I'm
Okay.
giving people till then
Oh,
to
that's
turn
right.
it in. Yep.
Okay.
But I will post them. I have them ready to go.
Okay.
Yep.
Thank you.
If I forget, email me. But
Okay.
okay. Let's clear all these.
So
Okay.
does that tell us that that W defines a subspace within R3?
Any vector will define a subspace wherever it lives.
Okay,
You just take one vector and look at the span of it.
gotcha.
What is your subspace?
Okay,
It's just all scalar multiples of that one vector, which is just a line through the origin. Okay. Unless, because there's always an unless in linear algebra, what's the one special thing I could pick if my one vector is the zero vector? Then what is the span of the zero vector, or what is the subspace that it generates?
Just the
The
zero.
origin.
Itself. You
Just
got it. Yep. Yep.
So I guess one of my questions would be, if the column space is just the range of the linear transformation, then why call it the column space? Why not just call it the range?
Because now we know it's actually a space, and if we have two things in the range and add them, we get something else back in the range. If we have something in the range and multiply it by a scalar, now we know we get something else back in the range. It just gives you a little bit more information about it, calling it a space. Okay. Let's see. I'll text. I will try this. So the other big one, null space of a matrix. Okay, I will go until the math stops me here, but we'll see. So the null space is set of things, set of vectors x, and I'm not going to go looking for that x vector hat, just take it by context here. Okay, with the property that ax equals the zero vector. Okay. So before, we just kind of thought of that as all the solutions to the homogeneous system of equations that correspond to the matrix A. Now, if I want to call the null space, technically, in order to call it a space, I would have to show you what? That it's closed under vector addition and scalar multiplication, right?
Yeah.
So if I do something like this, what happens if I have two things, x and y, that are in my null space? Okay, so when I have a times x plus y, I can distribute my a. So I get that plus ay. Okay, and if I start out by assuming that x and y were my null space, what's a times x? So if x is in my null space, I know that a times x is what?
Zero.
Okay. If I know that y is in my null space, that tells me that a times y is zero. And what is 0 plus 0? 0. So what this shows us is that if x and y are in my null space, then so is the sum, x plus y. Okay. One other quick calculation. If I take a scalar times my vector, where x is in the null space, then that scalar can come out in front. Okay. And that is c times, so if x is in my null space, a times x is 0. And what is c times 0? That is 0. Okay. So the null space of A is closed under vector addition and scalar multiplication. So it deserves to be called a space. So before we talk about a basis, one big question I could ask you is, hey, here's a matrix and here's a vector. Is that vector in the null space of A or not? And all you would have to do is what?
Augment it with 0. Set up a matrix and augment it with 0.
Even easier.
Oh,
That's
what is the
okay.
calculator?
So if so if I have A equals 1, 0, 1 minus 2, 2, 1. Okay. And I say, let's let X, okay. I should have mentioned the stuff we're doing now does not have to be with square matrices. It's any Rn and any number of things. Okay. So let's let X equal 1, 1 minus 2. Okay. And I would say something like, is X in the null space of A? Okay. So go back to my definition way up here. My null space is my set of things that has what happened when I multiply it by A.
Equal 0.
I get it. I end up at 0. Yep. So to see if a given vector is in the null space, all I do is I multiply it. So I just take 1, 0, 1 minus 2, 2, 1, and I multiply by, oops, somebody should have caught me on this. What'd I do wrong? Oh, I guess I could still technically answer the question, but it's not going to make you guys happy.
You put your X vector behind your A.
That's okay because I'm doing A times X.
Right.
But, okay, I'm going to do this, and then you're going to see what I did wrong.
Your
Okay.
handwritings are nice.
What's that? Oh, what I did wrong is I did my handwriting. Okay.
Oh, you can't.
That was a joke.
Okay.
You can't multiply those two vectors together.
Bingo. That's it.
The
Yep.
dimensions are wrong.
Exactly. Okay. So actually a good teaching opportunity, which was going to come next, is I'm going to tell you where the null space lives. But in this case, it can't possibly be in the null space of A because I can't multiply A by X. Okay. So what I'm going to do is I'm going to grab my eraser. And I'm going to do that. Well, actually, let me make it a little bit better altogether. Hey, this is a nice eraser. I'm easily amused. Okay. So all we do is we multiply. This we can do, correct? So I get 1 minus 2 is minus 1. And boom, I know that it can't be, correct? So 0 and 2 is 2.
Can I ask you a question?
Yeah, hang on. I'm thinking real hard now because I'm adding 1.
Oh, sorry.
That's all right. Okay. So not the 0 vector. So you go up here and you say, no, it is not. Okay, question.
So you did that, you made that correction because now A has as many columns as X has. Right?
Exactly. Yep.
Okay, just making sure.
That's right. So the way I had it, technically you could still answer the question, but it's kind of a trick question. X couldn't be in the null space of A because for this particular A, this 3x2 matrix, remember it's a 3x2 matrix. So as far as the linear transformation goes, it goes from R what to R what? 3x2 goes from R2
2?
to R
R2.
3x2 matrix, R2 to
R3.
You got it. Okay. So something I'm going to write down here in a second. Up here, oops, too far. The null space of A lives in the domain. Okay. The column space of A lives in the range. Okay. So if A is not a square matrix, those two things are different dimensions, and the null space and the column space live in completely different places. So if I have like a 2x4 matrix that goes from R4 to R2, the null space lives in R4, the column space lives in R2. And I wrote COL and I wanted C, or CUL and I wanted COL. I can't blame the technology. I can just blame my brain. I can blame the red cup. Column space.
I know what you mean.
Really, it's just Fresca. All right, so null space, set of things that get sent to 0 when you multiply by your matrix. Right now, the key question is, hey, here's a vector. Is it a null space of A or not? All you do is multiply it by A, see if you get 0 or not. And by 0, I mean the 0 vector, everything in sight is 0. Okay, not just the top slot or the bottom of your favorite, all of them. Questions?
Seems pretty straightforward.
Yep. So there's something else coming called the row space, which will not surprise you at all. Okay. I don't want to spend any time right now on it because we're going to learn how to find what's called a basis for it, which is actually really nice and easy. And at the moment, the row space is not as important as these other two. So the null space and the column space are kind of the big key ones right now.
That's like pretty much 2.8 then, from what I'm looking at.
Haven't talked about a basis yet, but yes. Okay. So the next big topic, and the big picture of it, it's really easy, but it's a very, it's one of the big words in linear algebra is what is a basis? Okay. So I'm going to erase this. Again, I'll put this on YouTube and you can watch it when you want to go to sleep. So a basis of a subspace is a set of vectors that have two properties: that they span the subspace, so that means you can get anywhere you want to go taking linear combinations of those vectors, and they are linearly independent. So the key result from that definition is that if you have a basis for some, and again, your subspace can be the whole thing, so it makes sense to talk about a basis for R3. In fact, we've talked about the standard basis. Okay. But the key thing about a basis, which kind of leads into 2.9 here in a little bit, if we have time today, we might. The key thing about a basis is that if you grab anything else in that subset, because they span, you can write that thing as a linear combination of your basis vectors. And the fact that they are linearly independent means when I go to actually do that solution and write them as a linear combination, I don't have any free variables showing up, and I can solve it in exactly one way. Okay. So kind of the key consequence of having a basis is that any vector in the space can be written as a unique, linear combo of your basis vectors. And that's what makes a basis handy. So if you think about the standard basis in like R2, well, they span so you can get anywhere you want to get. And since they're linearly independent, when you go to solve and get that linear combination, there's no free variable and you can solve it exactly one way. So that gives you kind of your uniqueness. Everything is a unique linear combination. Question so far? Okay, let me pull up one of these things over here.
Sounds a lot like I hat and J hat.
It's exactly, I hat and J hat are two basis vectors for your standard basis. Yep.
Okay.
Okay, so let me stop this one and go back to this. Let me make sure that's that.
Basis, are the basis vectors then going to create something that looks like the identity matrix?
When you do what to it?
Reduce.
You got it. Okay. All right, so look over here at the problems in the textbook. Look at, oh, yeah, we'll come back and do that. So look at 15 down here. Okay, so determine which sets and exercises 15 through 20 are basis for R2 or R3. I don't know why, but usually when they say the plural in mathematics, basis turns into bases, although it looks just like bases in baseball. Yeah, so as long as I know what you're talking about, I don't care how you pronounce it. Okay, so in 15, they say R2 or R3. So 15, we're looking at which one? Where do those things live?
2.
Yep, R2. So it may or may not be a basis for R2. So how do we check? I'll give you a hint. We're going to put those two columns into a matrix and row reduce. Okay. If we get what matrix, then it's a basis.
Identity.
If we get if we get the identity matrix out, that 1 0 0, oh, in fact it's R2, so it's going to be 1 0 0 1. Okay. If we don't get the identity, that means we have a row of zeros, which means a free variable shows up, and that means they can't span because it's not onto, and when you can solve it, you're going to have a free variable. Okay, so things are, when you can solve it, things are, it can be written as a linear combo lots of ways. But in this case, what do you think is going to happen? So just look at the vectors in 15. I got 2 of them in R2. Are they linearly independent? You know I'm going to ask you how you can tell. So when you just have 2 vectors, what do you look at?
They're multiples of each other.
You got it. So are those 2 multiples of each other or not?
No.
They are not. So they must be linearly independent. I got 2 vectors in R2 that are linearly independent. Got to be a basis. In fact, there is a theorem, I don't know if we'll write it down or not, but it's kind of lurking around in here that corresponds to these matrices that says if you're in Rn and you have n linearly independent vectors, then they must be a basis. Because if you have n linearly independent vectors, you're getting n different directions. And in Rn, how many do you got? You got n. Okay. So how about number 16 though? Look at those 2. If I'm doing it right, I think they are not linearly independent. They are dependent, correct? Because the first one is -2 times the second. So the span of those 2 vectors is actually what? It's just a line through those 2 vectors, which line up already. So there are places I can't get in R2, basically anything off of that line. So they don't span, they're not linearly independent. If I put those 2 in a matrix and row reduce, which you are free to do, and is technically probably the quickest way, well, it's probably quicker if you just notice this, but you just put those 2 in a matrix and row reduce, and you're going to get what? You're not going to get the identity. You're going to get a couple, you're going to get a row of zeros at the bottom. Okay. So for 17 and 18, I can't scroll this, but the way you approach it is you just make a matrix with those 3 columns, row reduce, and see if you get the identity. So they are a basis of R3 in 17 and 18. They're a basis for R3 if and only if the row reduction of that matrix with those columns gets you to the identity matrix. If not, that means you got a row of zeros, so there are places you can't get, so they can't span, and that means since it's square, you're going to have a free variable floating around and all that stuff. All this stuff is connected. Ooh, so another way that you can think about it is, for example, when we have 2 things in R2 or 3 things in R3. So there's another kind of theorem floating out there that says every basis of R3 is going to have how many things in it? Just guess.
3.
Every basis of R2 is going to have how many things in it? 2.
4.
Okay.
Well,
So
things you mean vectors.
yes. How many basis vectors, how many vectors it takes to form a basis?
Yeah, okay.
So you have a little bit of work to do, but you can actually prove that if a given basis has like 3 things in it for some space, then any basis has to have 3 things in it. If you have more, you lose linear independence. If you have fewer, then you can't span. Okay. Doing it remotely, I would say just take my word for it. You can read it in the book if you want to. But what was I going to say? Oh, so another consequence of like looking at 15, 16, 17, 18, when you have n things in Rn, so put them in a matrix and row reduce, or think about something we did recently that involved row reducing and getting the identity matrix somewhere. What else were we doing recently that involved doing that?
Inverting.
Inverses, that's right. So if you stick your vectors in as the column of a matrix, okay, they form a basis if and only if that matrix is invertible, if and only if it has an inverse. Which is the same as saying if and only if you row reduce it and you get to the identity matrix.
Nifty.
Because the only time it's going to fail is if one of those things is a linear combination of the others and they're not independent, or if I don't give you enough to span a place, and then you're not going to have enough rows to do it. But it's all connected. It's all connected in something in your book called the invertible matrix theorem, not just in your book, but in kind of any linear algebra textbook. Basically, all we're doing throughout the semester is we're taking the invertible matrix theorem and we're getting about 30 pieces to it, and each one is if and only if and only if. Okay, how do you feel about a basis?
Good.
Go. So two key things: linearly independent, and they span. So before I go on and talk about how to find a basis for a null space and a column space, look at the book again that I have up there and look at like just number 11. Don't worry about the numbers, okay? But it says give integer, it's a stupid way of saying where does our null space and where does our column space live is what they want to know. So for A, that's a 3x4 matrix. So the linear transformation that corresponds to it goes from R4 to R3. And my null space lives in the domain, so my null space lives in R what?
3.
Try the other one.
4.
It's
I'm
4.
at 4.
Yep. Okay. So a 3x4 matrix, it goes from R4 to R3, from R4 to R3. So my null space lives in the from part, the R4. My column space lives in the to part, the R3 part. The way I remember is the column space has to involve the columns of that matrix, and the columns of that matrix live where? They all have 3 pieces, right? So that's going to live in R3. How are we doing?
Can you say that again? The column space, there's 4 columns, but on number 11, there's 4 columns.
So in 11, there are 4 columns. So my input, my domain is going to live in R4 because my input involves a weight for each of those 4 columns. But my output world is going to be linear combinations of those columns, which all live in R3. So my output has to live in R3.
Okay, and so the column space lives in
the output world. Yep.
Okay.
Null space lives in the input world. Column space lives in the output world. Oops. How are we doing? 820. Okay.
Solid, I think.
Good. Okay, so I think all I have left today, let me see. So let me stop sharing this for a second. Because it kind of takes over my, oh, where'd it go? There it is. Yeah, so I only got 2 more things. If I get through 2 more things, I think we're in business. So let me just give you an example of how to find a basis for a column space and a null space. Okay. So let's go back to a whiteboard. All right, let me start with a new one. Oh, there it is. Okay. So how to find a basis for column space of A and null space of A. So I'm going to give you a hint. We're going to plug in A into our calculator and do what?
Reduce.
Row reduce.
Row reduce. Okay. So a basis, I can do this, for the column space of A, okay, is the pivot columns of A. So what I do, notice it's not the pivot columns of the row reduced version, it's the pivot columns of A. So I have to row reduce in order to find my pivot columns, and then I go back to the original matrix and grab those columns. So we'll do an example here in a second. Okay. That's actually easier than the null space. The null space is something you guys have already done. Okay. This will not surprise you. So a basis for the null space of A is the vectors that show up next to the free variables when we write the solution to AX equals 0. And I wrote that because I don't want to have to type out homogeneous. Okay. I think I'll just put a period there. I think it's good. Okay. All right, so let's take a look at, let's see what I got here. I'm just going back to the book to see if they have a decent one that we can steal. Yeah, in fact, I'm going to look at 23 in the book. Okay, so what they do is they assume that you can stick stuff in a calculator and row reduce at this point. I have complete confidence in all of you now. Okay, so let's go down here and let's say, so they say, oops, I need to do draw. Okay, so let's say A equals, this looks terrible, but they actually row reduce it for you. So 463. 554, 918, and -2, 12, -3. Okay, and they actually tell me that this thing row reduces down to, be with you in a minute. Okay. 1, 0, 0. So before I do anything else, is my first column a pivot column?
Yes.
Yes, it's always going to be, unless that first column I start with is all zeros, and that's kind of a stupid system of equations. Okay. 2, 1, 0. So I have another pivot column. Okay, so that what that tells me is that over here in my original, I keep the first one and I keep the second, because the second is not a scalar multiple of the first. Okay. And what comes next? Next, I have 6, 5, 0. So is my third one a pivot column?
No.
It is not. So that is telling me back here in my original that 918 is a linear combination of the first two already, so I don't need the third one. And lastly, -5, -6, 0. Okay. So what are my pivot columns in the row reduced form?
First and second.
First and second. Pivot there, pivot there. Okay. So that means I go back here and I just grab the first two. But remember, for the column space, I have to go back to the original matrix. I want the pivot columns of the original. Okay. So a basis for column space of A is the two vectors, that's a set symbol, 4, 6, 3, and I need the second one, which is 5, 5, 4. Okay. One kind of key thing is that a basis is not actually unique. Any given subspace has lots of different bases, but this is like, you know, the way, you know, any linear algebra teacher anywhere says find a basis for the column space. This is what they expect you to do. Okay. So what this is telling us is that we need the first two columns of A, but because the third and the fourth end up not being pivot columns, they must already be linear combinations of the first two columns. We don't need them. They're not linearly independent. They're not getting us anywhere new. Okay. So in this case, our column space has how many things in a basis? I got two vectors there. Okay. So that tells me that my column space is actually some two-dimensional set. Say plane in my column space lives where? R3. So it's a two-dimensional hyperplane in R3. Okay. So the algorithm for finding the column space, pretty straightforward. You just row reduce, find your pivot columns, but make sure you grab the pivot columns from the original matrix and not the row reduced one. Okay. Because, maybe I risk confusing you. Okay. So if you look at like a row reduced form over here, those two columns, if I were to grab those instead, I still get some two-dimensional space, but it's a different space. So the span of 1, 0, 0 and 2, 1, 0, the span of that is going to have stuff whose third component is all 0, because I can't take linear combinations of those and get off the 0 place, right? Whereas over here, the last component of those two vectors is not always 0. It is possible to have non-zero entries there. So the two spaces kind of look the same, but to make sure I'm getting the right one, you go back to the original matrix and grab those pivot columns there.
So would 1, 0, 0 and 2, 1, 0 be subspaces of the space that is defined by 4, 6, 3, 5, 5, 4?
Nope, it is a completely different space that is isomorphic. Okay. It looks and acts the same, but it's a different space, different orientation altogether.
Cool.
But hold on, how could
I'm holding.
How could these be bases if they're not linearly independent?
The first two are linearly independent, but only the first two, because they correspond to the pivot columns. But you are right. If I throw in the third and the fourth column, no longer linearly independent, so those four columns do not form a basis. They're not independent. But the first two do.
First two are.
Yep, the first two are the only two that I got that are linearly independent, because they're the only two that correspond to pivot columns.
I see.
The non-pivots, basically when you have a non-pivot, that is telling you that that column is already right up, it's a linear combination of the ones coming before it. Don't need it to get any place new.
Okay, I understand.
How are we feeling about column spaces?
Good.
Seems straightforward enough.
They are. Yep. Okay, so now let me show you how to find a basis for the null space. It's a little more involved, but you guys have already done this. So while I want to use the same row reduction. So what I'm going to do is I want you guys to actually think about augmenting that A with 0, okay, and then row reducing. And what I want you to do while I erase this stuff at the bottom is simply to take that RREF version and to write down the equations that correspond to. I want you to write the solutions in vector parametric form.
So like x1 equal to 2x2 plus 6x3 minus 5x4?
I want you to do that and then actually kind of factor those free variables out. And I want to see x equals x3 times a vector plus x4 times a vector. Okay.
Oh.
But yes, what you said is the way you would start. Yes. So let me grab that eraser. I'll make this video available so you don't have to write down all this stuff. I will wait a minute while you do that. And I can't see what you're drawing, so you can just draw funny faces or something if you want to. Oh, heck, they did something. Yeah, never mind. What did they not do here that I thought they had? Look at what they did on the right-hand side. What is that? What form is that not?
It's not consistent.
It's
Oh,
not
it is.
actually. It's not row reduced echelon form.
Yeah.
Because I just looked at it and assumed that
No.
what they would give me was,
Yeah,
okay?
it's not.
So it's not, because I have a leading one right there
Mm,
that has
two.
something above it, okay? So we could kind of do our back substitution and get around this. However, what I would rather do is actually just do row reduction for it. Okay, so plug either one of those into a calculator and see what comes out. Let's see, somewhere I have a calculator. Anybody have one handy?
Yeah, one in front of me.
All I have down here in my basement is a TI emulator, which would probably bring my little laptop to a screeching halt.
So it's, you ready?
Okay, nope, I'm not. Hang on, I gotta write this thing. Okay, you give me the first row or the first column?
Row is 1, 0, negative 4, 7.
Oops, negative. What the heck's going on here? Second row.
0, 1, 5, negative 6.
Third row.
All zeros.
I guess I knew that. Okay, now that is row reduced echelon form. So now I can write down, I'm going to skip a step here. I'm just going to move my free variables over to the right-hand side. Free variables being x3 and x4, okay? So x1 is 4x3 minus 7x4. See what I did there? I thought of setting all those things equal to 0, and then I'm moving my free variables to the right-hand side.
It's -4. Or on
Yeah, but I moved it to the right-hand side.
Oh, yeah.
Yep.
Right.
Okay. So x2 is minus 5x3 plus 6x4. And man, I would kill for this thing to get just a little bit larger. Okay. I'll go up here. Okay. So now what I meant was finish this thing up and put it into vector parametric form. So we have my solutions x. And remember, these are solutions to the homogeneous equation. So I'm augmenting with 0 that I didn't bother doing. Okay. So I have a free variable here. You remember how this goes? It's starting to look familiar. It's been a while. x3, and what happens when I factor out my x3? I have a 4 and a -5 plus x4. What happens when I factor out an x4? I have -7 and I have 6. See what I did? I want to pause there because that's the hard part, but that's stuff you guys have already done. Look familiar? Yay, nay?
So
Okay.
So the vectors 4, 5, and -6, 6, or -7, 6 are the basis vectors.
You got it. So what is happening here is this is just a different way of phrasing stuff we've already done. So if we look at this stuff here, this is telling me that my solution set, the set of things that get sent to 0, are all scalar multiples of that thing and that thing. Hang on here. What I do is I did something stupid.
You're going to have to tell me on this one.
Oh, no. Well, I'll figure it out. Hang on here. Oh, I know what I did.
0 and 0.
I forgot my x3 and my x4. Yep. You got it. So I have x3 equals x3.
And x4 equals.
And x4 equals x4. So down here, let me erase that real quick. I'm just going to add the missing pieces here. So that was 1, 0, and this was 0, 1. Okay. Oh, I can't let those are the worst brackets in history. I can't let that happen. Oh, I didn't know I could do that. Sorry about that. Everything else we said still works. These two vectors I'm after are going to be the ones that work. It's wild. I wonder why it does the whole thing. Okay, so what this is telling us, stuff we've already done, but slightly different way of thinking about it, is that these two vectors that are sitting out here in front of my free variables, those two right there, okay, since everything in my null space is a linear combination of those two vectors, it's x3 times one of them plus x4 times the other, where x3 and x4 are whatever I want them to be. This says my null space is the span of those two vectors. And if you think about how we kind of build it, look at that 1, 0 and that 0, 1 at the end that always show up when we do this. You know, you guys have seen this dozens of times at this point. That is enough to convince me that they can't be linearly dependent. They must be independent. So the vectors that end up sitting next to my free variables form a basis for my null space.
Cool.
Okay.
I'm confused about where where those last two values are coming from.
Which two values? The 1, 0 and the 0, 1?
Yeah, yeah.
That's because that's the ones I forgot down here when I wrote down my solutions. When I wrote down x1 and I kind of moved everything over, and x2 moved everything over. What is x3 and x4 are free? So what is x3 equal to?
X3.
Yep. So when I factor an x3 out of that, that's going to leave me with a 1. And x4 doesn't have an x3 in it, so that gives me that 0. And then vice versa for this one right here.
I see, I see.
So the two standard procedures out of this thing are, here are some vectors, you know, tell me if they are a basis or not of the space they live in. Basically, you just create a matrix and see if it's invertible, see if you can row reduce it down to the identity or not. Okay. Find a basis for the column space. All you do is find the pivot columns of the original matrix, that's your basis, and find a basis for the null space. So this one does take a little bit of work, but it's work that you guys have already done. Notice that my column space of A lived where? So it's on the previous whiteboard, but my column space actually lived in R3 because that's where my columns live. Where does my null space live? It is a span of things that are in, those vectors live in R4.
4.
Because they have 4 pieces.
Yeah.
Okay.
Got it. Yeah. I don't know what I was thinking.
So one thing that I'm going to get you on in a test problem, not on purpose, but it always happens, is that if I say at this point, because we get so used to finding like column space, a basis of a column space and a null space, I'm going to say something like, you know, is such and such in the null space of A? And what half the class is going to do is they're going to find a basis for A, and then they're going to see if they can write that such and such vector as a linear combination of the basis elements. But if you just go back to the definition, if I'm just asking, is one thing in the null space of A, what's the easiest way to check? Just multiply it by A and see if you get
0 vector.
0. Right. So asking for a basis for the null space or the column space is essentially finding all solutions. So if I'm just asking you to check one, that's usually more work than you need to go through, although you can still do it. Okay. But a basis is kind of finding all of them.
Okay.
Mr. Chen.
Yo.
Yeah. How this mean this one? How you have look like down here? You have S3 for -5, and after that you have 1, 0 under. I don't know how you have that.
Right. So that is the stuff over. Oh, hang on. Will this? No, never mind. Shoot. That comes from the fact that X3 and X4 are both free because they don't get to lead off rows in my row reduced. See over here in the bottom left? X1 and X2 are pivot columns, but X3 and X4 don't get to lead off rows. So they are free variables. So when I go to write my solution, since they're free, we always just say X3 equals itself and X4 equals itself.
Yeah.
Okay. So let me get a new whiteboard to show you what I'm doing there, because it's obviously, hang on. So let's say I had, yeah, let's do this. So let's say I ended up with a matrix that looks something like this. Yeah. My mouse is even worse than that. So let's say I had 1, 0, 1. No, I don't want to do that. I want something even easier. I want something in row reduced form. So let's say I had 1, 0, 0, 0, 0, 1, 0, 0. Let's say I had -3, 2, 0, 0. Okay, that row reduced echelon form?
Yep.
I believe it is. Okay. So if I want to find a basis for my null space, by the way, if that's my original matrix, I can find a basis for the column space. But if I didn't tell you what the original matrix was and just gave you the row reduced, I'm kind of stuck. I know the first 2 columns will do it, but I don't know what the first 2 columns would be if I didn't give you the original, right? But for null space, I can do this. So let's say, so this tells me that x1 minus 3x3 equals 0. The second row tells me that x2 plus 2x2 equals 0. And those are the only 2 real equations I have, right? Because I have a couple rows of zeros that aren't really terribly useful information. So this is telling me the top equation says x1, I'm solving for my leading variables in terms of the free. So I'm moving all my free variables. So I'm taking the free to the right-hand side. Okay. So down here, my x1 is 3x3. My x2 is minus 2x2. And how am I, sorry, that's supposed to be a 3. Sorry about that. Let me see if I can fix that. Come on. Okay. Well, at least I was consistent. Wrong one. Okay, so that was 3. So I know x3 is free. x1 has to be 3 times x3. x2 has to be minus 2 times x3. And since x3 is free, I end up writing that as x3 equals
x3.
x3. So now, when I kind of put together all the pieces, if I put back a step that I've kind of been skipping because we've done this, but let me put it in now because I've had a couple questions about it. I would write my solution in vector form like this. See what I did there? I just made those components of my 3 vector. And I factored out my free variable. In this case, I only have the one of them. And when I do that, I get 3 minus 2, 1. So in this case, what is a basis for my null space?
3, -2, and 1.
Bingo. Yep. So my null space is one-dimensional in this case because I only have one free variable. I have a basis element for every free variable that shows up, and the basis element is the vector that ends up sitting next to it when you factor those free variables out. Did that answer your question?
Yeah, even you the final you say the basic no, this means 3 minus 2, 1, right?
In this case, yep. So that right there. I also have 2 screens going on here, and this tablet kind of goes back and forth, and I'm losing my mind. So that one thing right there is a basis for the null space of A. Right there. Yep. You have a basis element for each free variable.
Yes, Mr. James, I mean we still put the question in the calculator, the matrix.
Uh-huh.
If after that we have the row reduce the answer. After that we we move like x1 equal Laplace, x2 equal Laplace, x3, and after that,
Yep.
we move,
And then you move your free variables to the right-hand side.
move free variable.
Yep. And then when it comes time to write the solution, each free variable gets written as equal to itself. Okay. And then you basically factor those two free, or how many free variables you have, you factor them out in front of like the other pieces. And it's those pieces that end up forming your basis vectors.
Move free variable. Okay. Thank you.
So look back a few weeks. This is stuff we've already done. It's just that now I'm pointing out to you that the vectors that actually sit next to the free variables, they're actually spanning the null space, and the way we build them, they're linearly independent, so they must be a basis.
And inversely, we just multiply that by the original matrix to determine whether that's in the null space or not.
Yeah, if I just gave you a vector and said, hey, is it in the null space? You would just multiply it by A and see if you get 0. And I guarantee you, if you multiply this A by that 3 minus 2, 1, you'll get 0. In fact, I can do it in my head right here. Yep, it works. It's like magic.